circuit shown above has been connected for a long time. Now, this is going to be your clue, because connected for a long time will make the capacitor fully charged. And if that's the case, no current is going to go through the capacitor branch. So no current can go through here. Okay, the switch is going to be in the open position. So that means that no current can go through R3 either. The circuit contains 3 resistors that are identical to each other, each of which has a resistance of R. And there's also going to be a capacitor of C and the ideal battery of potential difference VB. The switch is then closed. So a switch is then closed. Okay? So in terms of VB, what's the potential difference across the capacitor when the switch was open for a long time? So now the switch has been open for a long time. If the switch is open, that means there is no current in R3. Okay? So look, the current will basically leave the VB. It will go through R2. Then it's going to face 2 paths, both of which are going to be blocking it. So the current then cannot proceed, and therefore there's going to be no current in any of the resistors. So in this case, we're going to say that I of R2 is equal to I of R1 is equal to I of R3, all of which is equal to 0, I being the current here. So the current in the circuit is going to be a 0. Okay? And now the capacitor is fully charged. So it will receive the same voltage as the battery, since all the resistors don't get any current. Therefore, the voltage of the capacitor is equal to the voltage of the battery, which is called VB. Okay? That's part A. Let's go to part B. In terms of VB, what's the potential difference across the capacitor a long time after the switch was closed? So the switch has been closed for a long time. When they say a long time, that basically means that your capacitor is fully charged. And if it's fully charged, no current can go through it. Now what's going to happen is the following. The current is going to leave the battery. It's going to go through R2. Then it's going to proceed. It cannot go through the capacitor branch. It has to go through the R3. Then it's going to come back. It's going to go through the R1. And it's going to land back in the battery. And so basically, all the resistors get current. Okay, they all get current. Now, the capacitor, okay, is in parallel. Let me just erase this. The capacitor is going to be in parallel with R3. So the capacitor is in parallel with R3. Which basically means that whatever voltage the R3 gets, the capacitor also gets. So the voltage in the capacitor is equal to the voltage in R3. The question is, what is the voltage in R3? So you should know that R1, R2, and R3 are in series. So they will split the voltage equally, each one getting 1/3. So the voltage in R3 is equal 1/3 of the voltage of the battery. So the voltage in the capacitor is equal to the voltage in R3, which equals the voltage of the battery divided by 3. That's going to be the answer for part B. Moving on to part C, the current in R1 is I1. Okay. A student writes the correct equation. The voltage of the battery is equal to I1 times R1. So let's just rewrite it here. I1 times R1 plus I1 times R2 plus Q over C. Now look, the three resistors, R1, R2, and R3. Okay, so I1 goes in R1, R2, and R3 because they're in series, right? We know that. And essentially, what is this Q over C doing here? So you should know that Q is equal to CV, so V is equal to Q over C. That's the equation for the voltage in a capacitor. So, and we should know that this capacitor here is in parallel with R3. So it's going to have the same voltage as R3. So the V of the capacitor is equal to V in R3. Okay, and the voltage in each resistor is the same as the other one. So here V of R1 is the same as V of R2, which is the same as the V of the capacitor, which is the same as the voltage in R3. Okay, and the voltage in each component here is going to be 1/3. So the 1/3 of VB. So the V of R1 is equal VB over 3. The V in R2 is equal to VB over 3. The V in the capacitor is equal V in R3, which equals to VB over 3 as well. So is the equation good? Yes, the equation is good. Okay. Is the graph consistent with the equation? Let's take a look. Okay. Let me just erase this. So what's happening here is that as we go from A to B, we have to go through R1, which will result in a voltage drop, which is the case here, a voltage drop. Okay. Let's memorize that this voltage drop is equal to 2 ticks, right? So from here to here is going to be 2 ticks. Next up, we're going to go through the battery. And since we have 3 resistors, and if the voltage drop in R1 is equal to 2 scale marks, as we saw, right? 1, then 2. Then if we go through the battery, which equals the voltage drop of 3 resistors, we should then get up by 6 scale marks. So 1, 2, 3, 4, 5, 6. Perfect. Okay. Now we're going to go through this piece of wire, which means no voltage drop. That's why it's going to be a horizontal line. Then we're going to have a voltage drop in R2, which again must be equal to 2 scale marks. So 1, then 2. Then we're going to have a piece of wire with nothing, no voltage drop. Okay, all the way to D. Then we're going to be going through DE, the voltage drop of 2 scale marks again, 1, 2, because the voltage in the capacitor is the same as the voltage in R3. Okay. Then we're going to go back through the wire, which is E through A, which is no voltage drop. And of course, if you started here, you must go back to the same horizontal level. Okay. Good. So the graph is consistent with the equation. Yes, the graph is consistent with the equation. I just explained what's happening here. So basically, there is a voltage drop in the resistor / capacitor by 2 scale points each, since they have the same voltage, and a voltage rise in the battery by 3 times amount. Okay, since VB is equal to VB over 3 plus VB over 3 plus VB over 3, and you start and end at the same voltage point, which, as we can see here, you start here, you end here, right? Which is 2 scale marks above the origin. Okay, as we saw that Q over C is equal to the voltage in the capacitor, which equals the voltage in R3, which equals the voltage of the battery over 3. Okay, I1 times R1 is equal to the voltage in R1, which also equals to VB over 3. I1 times R2 is equal to the voltage in R2, which equals to also VB over 3. So the equation is consistent. Part D. Okay, we have another equation now. Indicate whether the equation supports your reasoning in part B, and explain why the equation does or does not support your reasoning. Okay, so basically, what this equation is VB times R2 over R of the circuit is equal to VB of the battery minus VB times R1 over R of the circuit minus Q over C. Now Q over C, by the way, is just the voltage in the capacitor. And the voltage in the capacitor is just equal to VB times R3 over R of the circuit. So essentially, we can say that if we move these guys here, it's going to become plus sign. So it's like saying plus is equal to VB. So VB is equal to essentially the voltage across R2 and the voltage across R1 and the voltage across R3 all combined, which makes sense, right? Like I said, the voltage across R3 is the same as the voltage across the capacitor. They have the same voltage as each other because they are in parallel with each other. So the equation is consistent, right? The equation is good, right? Indicate whether the equation supports your reasoning in part B. In part B, we said that what's the potential difference in the capacitor after a long time the switch was closed? That we said was when the capacitor and the R3 had the same voltage. So VC is equal to voltage in R3, and which was equal to VB over 3. So yes. So yes, it supports the part B reasoning. Okay. Explain why the equation does or does not support your reasoning using physics principles. It does, since VB is equal to the voltage across R1 plus the voltage across R2 plus the voltage across the capacitor, which is the same as the voltage in R3. Okay, good. That was part D. Let's erase now. Okay, part E. Resistor R2 is now replaced by a second capacitor that also has a capacitance of C, and the switch is going to be left open for a long time. what's the potential difference across each of the capacitors? Let's go to this figure. So now instead of R2, we're going to be putting capacitor. The switch has been open for a long time, and the capacitor is going to be fully charged. There is no current in the circuit. Both capacitors are fully charged, and they are in series with each other, so they will split the voltage among them equally. Split the voltage of the battery, so each gets VB over 2. Okay, this one gets VB over 2. This one here gets VB over 2, and if you add them, you will get VB of the battery.